All right, let's dive into MVCC, Multi-Version Concurrency Control. It's one of those things you don't think about, but it really makes everything we do online possible.
Right.
And you sent in some really interesting stuff on this, from like university lectures to talks by engineers at Postgres and CockroachDB.
Mm-hmm.
And even that talk on why county can be so slow in Postgres.
Oh, yeah. That was a fascinating one. It's a really great example of how something so simple on the surface can be really complex underneath in the database.
Exactly. So let's break it down. What is this MVCC thing?
Yeah.
Why is it important? And what are some of the trade-offs we have to think about?
Okay. So imagine you're trying to edit like a giant spreadsheet with someone else at the same time.
Right.
You change a number here, they add a row there, it'd be total chaos.
Yeah.
Databases face a similar problem. It's called the phantom problem.
Ooh, the phantom problem.
Yeah. And essentially it's the challenge of making sure that transactions, the individual units of work that happen inside a database, don't interfere with each other. Because if you don't have some kind of control mechanism in place, you could end up with data that's completely out of whack.
I see. So the problem is that like one transaction might be making changes based on a view of the data that's no longer accurate.
Yes.
Because another transaction has come in and messed with it.
Exactly. Yeah. And that's exactly where MVCC comes in. It's like giving each transaction its own little isolated view of the database, kind of like a snapshot in time. So even if other transactions are doing their thing, making changes, each one sees a consistent picture.
Right. So instead of constantly locking and unlocking things, which would make the whole system super slow, MVCC is a way to let everyone play in the sandbox together without messing things up.
Yeah, the key idea is that instead of overwriting data directly, the database keeps multiple versions of each row around, like a history log.
So some of the lectures you sent mentioned these things called version chains, which is, I guess, how these different versions are tracked.
Yeah.
Is that right?
Yeah, you can think of it like each row has this chain of versions, like a little timeline. And when a transaction starts, it sees a specific point in that chain, making sure it's working with a consistent snapshot. Now, there are different ways to actually manage these chains.
Okay.
And they all have like pros and cons.
So one that was mentioned in the lectures is append-only.
Right. Append-only is like the simple one. You just add new versions to the end of the chain. Easy to understand.
Yeah.
But obviously, these chains can get super long over time.
Right, especially in a database that's changing all the time.
Exactly, especially if you have a lot of updates, and that can lead to performance problems.
I see. And Postgres uses that append-only approach.
Yeah, Postgres does. It works well in a lot of cases, but it can be a real bottleneck if you have a ton of writes going on.
Okay, that makes me think of that talk about why count can be slow in Postgres. That was the Uber case, right?
Yeah. Uber actually hit a wall with Postgres's MVCC because it turned out that with these long version chains, counting every row was incredibly slow.
Yeah.
And they ended up switching to MySQL because MySQL's version is better for those high update situations.
Interesting. So different MVCC implementations for different needs.
Yeah. Yeah, exactly.
Cool. Okay, so what are some of the other ways to handle these version chains?
Well, there's time travel.
Okay.
That's where you keep old versions in a separate place, kind of like an archive. It's easier to access older versions, but it might mean that they're stored on slower storage.
Right, because it's not the hot data anymore.
Exactly. So it's a trade-off.
Right.
And then there's delta storage, which is a pretty neat one. It's kind of like using Git for your database. You just store the differences between each version, not the whole row every time.
That makes sense. That's got to be much more efficient.
It is for storage space, yeah, but it makes the logic to piece it all back together more complex, so there are definitely trade-offs.
Yeah. Okay, so we've got all these different versions being tracked in chains, but what about indexes? Those have to point to the correct version of the data.
Yeah, that's a really good point. You can't forget about indexes. They're super important for performance. And with MVCC, things get even more interesting because you have to make sure that when a transaction is using an index to find data, it's being directed to the right version of that data.
Right, the version that belongs to its snapshot.
Exactly.
So how do you do that?
There are two main ways. One is using logical pointers, which are kind of like fixed ID numbers that never change even if the actual data moves around. So the index points to that ID number, and then that ID number leads you to the right version. And the other way is to use physical pointers, which always point to like the tip of the version chain.
So if you use logical pointers, the index itself doesn't need to change, even when you update the data.
Right.
It just always points to that same ID. But with the physical pointers, you're constantly having to update the index to point to the new head of the chain.
Exactly. And this is actually another reason why Uber had trouble with Postgres, because Postgres uses the append-only approach with physical pointers.
Oh.
So every time they updated something, they had to update all these indexes, and it was just killing their performance.
I see. So MySQL, which I'm assuming does something different, was a better fit.
Yeah. MySQL uses a different locking model and indexing approach that's not as affected by all these index updates.
It's so fascinating. It's amazing to see how all these pieces fit together. But with all these versions being created, doesn't the database like fill up with junk eventually? Like, how do you clean all this up?
Yeah, that's a great question. And that's where garbage collection comes in. You have to reclaim that space taken up by old versions that nobody needs anymore.
Right.
Just like you need to clean up your hard drive every now and then.
But how do you know which versions are safe to delete? Like, what if you delete a version that some transaction still needs?
Well, there are some really clever mechanisms to make sure that doesn't happen. One common way is something called tuple-level garbage collection, where you have these background processes,
Okay.
often called vacuum threads, that scan the database and figure out which versions are no longer needed.
So they're just kind of constantly sweeping through and cleaning things up.
Yeah, pretty much.
Okay.
And there's another approach called transaction-level garbage collection, where each transaction kind of keeps track of the versions it messes with,
Right.
making it easier to clean up later.
So each transaction is responsible for its own mess in a way.
Exactly.
That's interesting.
Yeah.
But with everything happening at the same time, how does it actually keep track of what's still needed and what can be thrown away?
Well, it uses some pretty clever techniques to manage it all. One key idea is to use something called transaction IDs. So each transaction gets its own unique ID number, and the system keeps track of the oldest active transaction ID. Anything older than that can be safely removed.
Oh, so it's like a cutoff point.
Yeah, exactly.
Wow. This is all really, really cool. But I have a feeling MVCC isn't perfect, is it?
Well, you're right. It's not a silver bullet. It's really powerful, but it has some quirks, and there can be anomalies, like the right skew anomaly, which we haven't talked about yet.
Anomalies. Okay, now I'm definitely intrigued. Tell me more.
Okay. Imagine you have a database that keeps track of marbles, and each marble can be black or white.
Okay.
Two transactions start at the same time. One wants to change all the white marbles to black, and the other one wants to change all the black marbles to white.
All right. Sounds simple enough.
Now, under MVCC, both of these transactions see a snapshot of the database where they see the same starting state of the marbles. So each one makes its changes based on that snapshot, thinking it has the latest information.
Right. Because of that snapshot isolation thing.
Exactly. The problem is that when these changes are written back to the database, there's no conflict detected, because they were each working on a different version of the data. So the first transaction successfully flips all the white marbles to black, and the second one successfully flips all the black marbles to white.
Oh. So what happens to a marble that was originally white?
It gets flipped twice.
Right. It ends up back as white, like nothing ever happened.
Exactly. And now your database is in an inconsistent state because technically, you flipped everything.
That is mind-bending. So MVCC, while trying to help, can actually create these weird inconsistencies.
Yeah. It shows that MVCC isn't a magic solution. You still have to be aware of these potential issues and design your database carefully to avoid them.
That's a good point. Okay. This is all really interesting, but one of the things you talked about something called LSM trees. What are those, and how do they fit into all of this?
LSM trees, or log-structured merge trees, are another really cool way to handle data storage and indexing in a database. They're especially good when you have a lot of writes happening, and they're becoming more popular in systems like RocksDB and LevelDB. It's a whole different way of thinking about managing data, and you can even use them together with MVCC.
That's really cool. But I think we'll have to save that discussion for later because I'm already feeling a little overwhelmed.
Yeah, this is a lot to take in.
Yeah, it is. Okay, so before we were talking about LSM trees, and you said they're good for like lots of writes, which is kind of the opposite of what we saw with Postgres, right?
It is interesting, yeah, how different systems come up with different solutions for their problems. LSM trees are all about making writes fast.
Okay.
By minimizing how much you have to write randomly to disk, which is slow.
Right. Right. So how do they do that? I'm picturing like trees made of logs or something.
Well, no logs, exactly, but they organize data in sorted files. They're often called stables.
Okay.
And when you write new data, it it gets added to this in-memory thing, like a log.
Mm-hmm.
And once that fills up, it's written to disk as a new SS stable.
So it's kind of like batching up the writes and then writing them all at once.
Exactly. That's much faster than doing lots of small writes.
Yeah.
And as more SS stables are created, they get merged together in the background.
Okay.
It's a process called compaction.
Gotcha.
Keeps things organized and efficient.
I see. So a bit more complicated, but much better for write performance.
Mm-hmm.
But how do LSM trees connect to MVCC? Are they like a replacement for version chains?
So LSM trees themselves, they're not really about versions, but you can use them to implement MVCC.
Oh, interesting.
If you add versioning information into the SS stables,
Right.
then the LSM tree can basically store multiple versions, and that lets you do snapshot isolation with MVCC. So you can have a system that has both the fast writes of LSM trees and the concurrency of MVCC. That's cool.
Yeah, and that's becoming more and more popular, especially for things like, ingesting huge amounts of data or real-time analytics where you have tons of writes.
Makes sense. It's amazing how all these different parts of a database can be combined in different ways to make things work better.
Yeah, it really is. And as technology changes, we're going to see even more creative ways to manage data consistency and concurrency.
Yeah.
Actually, remember when we were talking about NVRAM earlier?
Yeah, non-volatile RAM, that super fast memory that doesn't forget anything when you turn off the power.
Right, exactly. And that technology, it could really change how we do MVCC.
Okay, now I'm really curious. What kind of impact are we talking about here?
Well, think about it.
Yeah.
If you can store those versions of data in NVRAM, it's so much faster than disk,
Yeah.
right? So
Yeah.
accessing those versions, reading them, writing them, it becomes way faster.
So it's like MVCC on steroids. Pretty much, yeah. And garbage collection could get easier too, because now you don't have to scan through all that data on disk to find what to delete. You can track it more efficiently in NVRAM.
Okay, so it's not just speed, it's also efficiency. Less overhead. Are there other ways you think NVRAM could change things?
I think it could change how we even design MVCC. We might not need those append-only version chains anymore.
Really?
You could come up with new ways that take advantage of persistent memory, maybe even integrate versioning directly into the storage itself.
Wow. So it's like this technology is going to rewrite the rules of how we do databases.
It could, yeah.
I'm starting to feel like a database nerd just thinking about all the possibilities.
It is pretty exciting. There's a beauty to how all these complex ideas work together to solve these real problems.
Definitely. Okay, before we go too far down the database rabbit hole, I want to come back to the right skew anomaly for a minute. You gave us that example with the marbles, but can you give us something a little more concrete, a little more real world?
Sure. Let's imagine a bank, right?
Okay.
We've got two customers, Alice and Bob. They both have $50 in their accounts.
Right. Classic banking scenario. What could go wrong?
Well, there's a rule that you can't go below zero in your account. Makes sense, right?
Yeah, definitely. No overdraft fees.
Right. Now, Alice and Bob, they both decide at the same time to transfer $60 to Charlie.
Uh-oh. I see where this is going.
So they each start a transaction to make the transfer, but remember with MVCC,
Yeah.
each transaction sees the database as it was at the beginning.
Right, their own little snapshot.
Right. So both Alice and Bob, they see $50 in their accounts.
Right. But they're each trying to transfer more than they have.
Exactly. And because they don't see each other's transfers because of those snapshots, they both succeed. So Charlie ends up with $120, which seems fine.
Right.
Except Alice and Bob should now have negative balances.
Whoa. That's messed up.
Yeah. The database is now inconsistent.
Yeah.
That rule about not going below zero, it's been broken.
So MVCC, which is supposed to prevent these problems, actually created one.
It just shows that MVCC isn't perfect. You still have to understand its limits.
Yeah. Okay.
Yeah.
This is all really fascinating, and I want to keep learning more, but I think we should take a break. When we come back, I want to hear your thoughts on where all this is going in the future. With new tech like NVRAM coming out, how do you see MVCC evolving? So we've really gone deep on MVCC, all those version chains and indexes, all the different ways it works, and even those weird anomalies like right skew. But before we wrap up, I'm curious about, what's next? What's the future of all this? With things like NVRAM changing the game.
It is a really interesting time for databases. Yeah, that line between memory and storage is getting blurry. And that opens up all sorts of possibilities for how we handle, keeping data consistent when lots of things are happening at the same time.
Right. You mentioned earlier that NVRAM could really change how we implement MVCC.
Yeah.
What kind of changes are we talking about? Like, what could be different?
Well, one big thing is how we manage those version chains. Right now, they're often stored on disk,
Okay.
which is, slow. But with NVRAM, we could maybe keep those chains in memory.
Ah, so they'd be much faster to access.
Exactly. Reading and writing those versions would be way faster.
That makes sense. What about garbage collection? Could that be improved with NVRAM too?
Oh, definitely. Right now, garbage collection can be a real pain. You have to scan through all this data on disk to find what you can delete.
Yeah.
But with NVRAM, we could track those version lifetimes much better. So garbage collection could be more efficient, less disruptive.
Okay, so it's not just speed, it's making the whole process smoother.
Exactly. And I think NVRAM could even change how we think about MVCC altogether. Maybe we don't need those append-only chains anymore.
Interesting.
We could come up with completely new designs, really take advantage of persistent memory, maybe even make versioning a part of the storage itself.
Wow. It's like we're on the verge of a whole new generation of databases.
It really feels that way.
All right, so to sum up, MVCC, it's this incredibly clever way to make databases work when lots of users are accessing data. It keeps everything consistent, prevents all sorts of problems,
Right.
and it does it all with versions, giving each transaction its own view of the data.
Like its own little time machine.
Exactly.
Yeah.
We've seen that there are different ways to implement it, each with its own strengths and weaknesses.
Right. And we have to remember those indexes. They're crucial for performance.
Definitely.
Right.
And even though MVCC is powerful, we saw that it can have some quirks, those anomalies like the right skew anomaly.
It's not a perfect system.
Right. But with new technology, like NVRAM, MVCC could become even more powerful, more efficient.
The future of databases is looking very exciting.
I agree. Well, I think we've covered just about everything on MVCC. Any last thoughts?
I think the main thing is, for anyone working with databases, MVCC is something you really need to understand. It's fundamental, and if this has sparked your interest, I encourage everyone to, dig into those materials you send in. There's so much more to learn.
Absolutely. And on that note, until next time, happy diving.